Okay, this is a demo video for showing how to use the open circuit so that you can simulate some of the design problem or even like the non-ideal property of open. So let's start it with a new design. The design is you have to go to get open. Of course, the open you have first to select voltage source for the positive and the negative supplies. So there will be positive and the negative supplies here. So you get positive, negative supply, and here okay, and negative supply, and we call it output port VCC and VEE. That's for the power supply. Okay, now we can go to get the universal open model. The universal open model is in the open, and you go into it, go to the end. Of course, here are all the open have been modeled and established by ADI. So there are so many opens here, but we need to use the open universal open model 2. Okay, and in the universal model 2 you can basically set all the ideal open with some non-ideal characteristic. So this is the open here. Of course, the open has 5 pins minimum, right? 2 input, 1 output, and 1 positive supply, the other one negative supply. So we have VCC here and also VEE here. Okay, so the power has been applied to it. And how much we need? We need 50 volts. Okay, that's for 15 volts. Now we have positive, negative supply, and now let's look at how can we complete this design. Alright, so before we go further, let's check what is the universal open model 2. Go to the example here, and then you go down here in the educational, you have universal open 2. Here it tells you you have 4 levels: level 1, level 2, level 3, level 4. Okay, but basically most of the cases we use level 2. Level 2 gives you a single pole open with 1 internal node, and the slew rate limit, output voltage, current limit are set by all these parameters. Here, the DC gain bandwidth product, slew rate, current limit, output stage saturation voltage, VOS offset voltage here, and also the input impedance. Okay, so that's for the definition of the universal open. Okay, now so if for example I want to complete the design for non-inverting case, so this is R2, R1, R2, and of course I need the voltage source as a signal. So let's go to the voltage source. That's for this signal. and there are ground and okay, so I didn't put any load resistance here. Trim it. Okay, now the circuit is done. For example, we already know if I have 9K here, okay, 9 kilo ohm, and this is 1 kilo ohm. Then I have non-inverting design, so of course the output will be 1 plus 9 divided by 1. 9K divided by 1, that's 10. So the voltage gain will be 10. So let's look at an output signal here. This is the out. Okay. And this is the in. Let me put like input for 0.1 volt. Not setting this default properties, I have to check if it's in level 2. So now you see here, alright, indeed it's already in level 2. I can use, of course I can change it into like level 2 other levels. Level 2, you can change it to level 1 to level 4. And the value here, now the gain is 1 meg. That is 120 decibel. And gain bandwidth is 10 meg. Okay, this is typical. Okay, and the slew rate here is 10 meg. Okay, that's per microsecond you have 1 volt. And the limit, I limit is 25 milliamp. That means you can have 125 milliamp output. And the input impedance is 500 meg. Of course we can change it, alright? So this is level 2. So let's check how can you get the result. Here, got here. So we can check DC up and run it. Now you can find out the V out is 0.999992. Of course, it's not 1 volt, but the input is 0.1. So 10 times should be 1, right? Why it's not 1? Because it's not, the gain is not infinite. Okay, and also there are current flowing into the input. You see here, number 2, number 3, there are current flowing in. Of course, here. Okay, and the flowing current is definitely not 0. That's for U1. Now if I change this input impedance to 50 meg, of course the current will be larger. Now you see here, alright, so you see the input current becomes larger here, Ix here. That's 1.5 milliamp. Okay, 1.5 milliamp. Okay, and If I change it back to 500 mega ohm, here this is still 1.5 milliamp. Okay, that's current flowing from here. Okay, and the current is flowing through the V3 is here, minus 2 times 10 to the minus 10. If I change it to 50 meg, then it should be 10 times. Now here you see V3 10 times, minus 2 10 to the minus 9. Of course, so this can be changed. We definitely can change the input impedance. Okay, and if I change the DC gain to 0.1, right? And of course, here you see there's originally is 0.99992, now it becomes 0.9999. Okay, because the DC gain is smaller, it will not be the same. Okay, so you can just by playing these numbers, you can set up the condition of the op-amp. Of course, the offset voltage, I can set it as like 5 millivolt. Then the output will be affected by the offset voltage. See? Wow. Now the output is 1.0499 because you have offset voltage. Let's go back to set it to be 0. Now it will go back. Now it go back to Vout is 0.999992, right? Okay, that's a typical op-amp you can do. Okay, let's check. If I put a sinusoidal here, the offset is 0, amplitude is 1, and the frequency is 1K. And what we will get, because it's 10 times, the output should be 10. Stop time, 10 milliseconds. Okay. MU. Now you can run it. You add propane. Here add trace V in and add trace V out. You see, now this is 10 volt, this is 1 volt. That's 10 times, right? And of course, I know if I change the frequency to the bandwidth limit, then you will have problems, right? So if I change to 1 megahertz, MEG, and the simulation MU and 1 mu, and let's see what will happen. See, the input is 1 volt, but the output becomes less than probably 1.8 volt. So the bandwidth limit has limited the gain of the circuit. That's typical. And we know for the gain of 10, you can probably hold to 100 kilohertz. So now let's go to 1K and do the simulation again. 1K we have 100K we have 10 micron, 100 micron. Okay, you see, now the gain is still 10. That's the maximum frequency you can use because the gain has been increased to 10. So the gain bandwidth limit has limited this open response. So that's what you can get from this result. Okay, now as you recall, if I use this circuit as some other purpose, like for integration, so I put an integrator resistor here, then the circuit will become an integration circuit, and I put, this is like micron, so 1 mu, and we know the circuit will limit the response of the circuit because this integration constant. Alright, now the gain becomes 1. Why? Because this 2 R times C, the time constant is what? It's 1K, right? So 1K is 1K, so the gain is 1. This time constant is 1 millisecond, right? So here is 1K. So it reduced to the gain to 1. Alright? So based on this, you should be able to do a lot of design and analysis. And of course, if I want to check what's the output limit current can give you, what kind of effect you can have, then I will put a low resistor here. We note the current will limit the output. So now for 10 volt, if I give you like 10K, then 1 milliamp. If I give you 1K, that's 10 milliamp. So if I put 0.5K, then the output amplitude should be restricted. Okay, it's barely 2 milliamp. So if I keep going down, still here, keep going down, 100. Oh, because it's 1 volt, I'm sorry. So 1 volt, then it should be 10. Okay, that's why the signal becomes limited by the current. The current cannot give you so much. Output is limited, it's clamped, so it becomes square wave. So if I go to 20, still 50, now it backs to 1 volt, right? So this obviously this current limit will give you a limitation on the op-amp performance. Alright, so from this simple demonstration, you can use the universal op-amp tool to do a lot of simulation you want here. That's for your op-amp demonstration.